Hello everyone. In today's session, I'm going to discuss about crystal field theory, in short CFT. Let us start our session. First we see introduction of crystal field theory. The crystal field theory was first introduced by scientists Bethe and Van Leek in 1930 and applied mainly to ionic crystals. On the basis of this theory, a complex is regarded as an aggregation of central ion surrounded by other ions or molecules with electrical dipoles. This theory does not consider covalent bonding. The modified theory, which includes covalent bonding, is called ligand field theory. This theory was used to explain the colors and magnetic properties of crystalline solids. Next we see assumptions of crystal field theory. In a complex, transition metal ion is placed in the center and it is surrounded by ligands with lone pairs of electrons. Second, the ligands are either negative ions like Cn minus or Cl minus, or they are neutral molecules like water, ammonia, and they are considered as point charges. If the ligand is neutral molecule, then the negative end of the dipole is directed towards the metal ion. Third assumption, there is no interaction between the metal orbitals and ligand orbitals. Fourth, the attraction between metal ion and the ligands are purely electrostatics, that is, the bond is 100% ionic. Fifth, the number of ligands and their arrangement around the metal ion determine the nature and strength of the crystal field. And the last assumption is the degeneracy of d orbitals of the free metal ion is removed by the ligands when a complex is formed. Here we all know that the metal consists of 5 d orbitals, and which are dx square minus y square, dz square, dxy, dyz, and dxz. Here we see the shapes of d orbital. All the 5 d orbitals are not identical, and there are in fact two sets of d orbitals. The dx square minus y square and dz square orbitals form one set and have lobes lying along the mutually perpendicular xy and z axis. The dxy, dyz and dxz orbitals form second set and have lobes pointing between the axes. Then here we see group theoretical symbols. The dx square minus y square and dz square orbitals are collectively denoted as Eg, and the dxy, dyz and dxz orbitals are denoted as T2g. The symbol T means there are three degenerate orbitals, that is dxy, dyz and dxz, and the symbol E means there are two degenerate orbitals, that is dx square minus y square and dz square, and the degenerate means equal in energy. The symbol G stands for G-rad, that is even the orbital is said to be G-rad if it is centrosymmetric, that is it has the same sign of the wave function at the same distance in opposite direction from the center of symmetry, while the symbol U stands for ungirate, that is uneven. The orbital is said to be ungirate if it changes the sign of the wave function at the same distance in opposite direction from the center of symmetry. The next point, degeneracy of d orbitals means the splitting of d orbitals. In a free ion, the 5 d orbitals are degenerate, that is energetically equal, and electrons which occupy such orbitals according to the rule of Hund's rule of maximum multiplicity. CFT is basically concerned with the effect of different arrangement of surrounding ligands on the energy of d orbitals. Electron pairing energy. Pairing energy of electrons can be defined as the energy required to transform two electrons with parallel spin in different degenerate orbitals into paired electrons in the same orbital. Alternatively, electron spin pairing energy is the transition from two orbitals in one orbital which is characterized by a decrease of electronic repulsion. So, it is the energy evolved, or it is the energy of stabilization, and which is denoted by a symbol P. The pairing energy P depends upon two factors, that is repulsion between electrons occupying the same orbital decreases with increasing size of the d orbital due to decreasing electron densities but remain almost the same in period. And the second is loss of exchange energy due to pairing. Then we see strong and weak ligand field splitting. In an octahedral complex, if the value of 10 dq or delta 0 is large, then it is called as a strong field splitting and the complex is called as a strong field complex. While in an octahedral complex, if the value of 10 dq or delta 0 is small, then called as weak field splitting and the complex is known as weak field complex. The magnitude of 10 dq or delta 0 depends upon three factors, that is nature of ligand, the charge on metal ion, and whether the metal ion is in first, second or third row of transition elements. The ligand which cause only small degree of splitting are termed as weak ligand, and those which cause large splitting are called as a strong ligands. Then here we see low spin and high spin complexes. The complexes formed by strong ligands, that is strong field complexes, which have the minimum number of unpaired electrons. So, such complexes are called as low spin or spin paired complexes, while the complexes formed by weak ligands, that is weak field complexes, have the maximum number of unpaired electrons. So, such complexes are called as high spin or spin free complexes. Then the most important point is crystal field stabilization energy of octahedral complexes, shortly called as a CFSE. The total decrease in energy caused by the splitting of d orbitals and their occupancy by electrons is called as crystal field stabilization energy, that is CFSE. In case there is pairing energy involved, it is added to the CFSE. Pairing energy is always the energy absorbed when two electrons neutralize their spins. The CFSE can be calculated by using the formula, that is minus 4 dq into number of electrons in T2g orbitals plus 6 dq into number of electrons in EG orbital. Here we see the CFSE for D1, D2, D3, D8, D9 and D10 systems. First, D1, the CFEC will be equal to minus 4 dq into 1, which is equal to minus 4 dq. For D2 system, we get minus 4 dq into 2 equals to minus 8 dq. For D3 system, minus 4 dq into 3 and we get minus 12 dq. While D8 system equals to minus 4 dq into 6 plus 6 dq into 2 and plus 3 pairing, we get minus 12 dq plus 3 pairing. For D9 system, we get minus 4 dq into 6 plus 6 dq into 3 plus 4 pairing, and finally we get minus 6 dq plus 4 pairing. And the last, for D10 system, we get minus 4 dq into 6 plus 6 dq into 4, and which is equal to 0. In the above cases, crystal field stabilization energy will be the same for strong field and weak field complexes. For a D10 system, although 5 electrons get paired, they create a spherical crystal field around the metal ion, and the net crystal field stabilization energy is 0. The crystal field stabilization energy for D4, D5, D6 and D7 systems in strong field and weak field octahedral complexes are different. They can be calculated by using the crystal field stabilization energy formula. Thank you.